Good morning, evening, afternoon, breakfast, dinner, midnight snack, everyone. My name is Alex Chabot-Leclerc. I'm a colleague of Eric Olsen here, who will be doing this NumPy tutorial. Sorry for the delay. We had some last-minute tech challenges. So what's going to happen is I'm going to go away. I'm not going to be away, but I'll be there to answer your questions. My colleague Matt Davis is also in the chat. He'll be there to answer your questions. And Eric will be the master of ceremony for everything else. I'm sorry I was not able to pull everyone into the session like I promised. If I did that, I would pull in everyone from the tutorial that's happening right now, and I'm sure they would be very upset. So, not doing that. So, Eric, the floor is yours.
Okay, good morning, everyone. Okay, so we're going to talk about numerical computing with NumPy this morning, and a lot of it is going to be basically focused on the NumPy library, but also the matplotlib library, because that's the interesting part, is being able to see what we have in our arrays. And so we're going to start out with matplotlib, show you how to display some stuff on your screen, and we have a chicken and egg problem where we've got to show you enough NumPy to get some stuff on the screen, and then once we can get stuff on the screen, then we can actually jump into NumPy and talk about it a little more in depth. So this first part is going to be matplotlib. Now, the way I like to teach this is you all have the slides, and I will talk a little bit about the slides, but what I'm going to do is try and follow the slides in IPython, typing as I go, so that you can see what's happening with IPython. And if you want to get into IPython, you can follow along, or you can also follow along in a fresh Jupyter notebook, typing in all the stuff that I'm going to type in. I will try and move pretty slowly so that you can keep up. And pause and come back and check the chat and the questions. Unfortunately, I don't have 3 or 4 monitors to show everything at the same time. So that's what my helpers are for, to answer your questions in the background and let me know what's going on with everything. So that said, let's get started with IPython, and we'll jump right into some of this. So if you have EDM, and I'll have to, one moment, change what I'm presenting. Where is that? Okay. Share my screen. There it is. I'm going to just share the entire screen. Okay. So I just pulled up a command prompt right here. And I'm going to start my Python environment. And depending on how you set things up, you're going to have a different environment to set up. You essentially want to get to where you could type Python and get a Python prompt. But instead of doing that, what I want to do
Eric?
is type, yep.
Can you make is it easy to make the font of this terminal larger? There we go.
That better?
Yes, that's wonderful. Thank you, Eric.
Okay, thank you. So instead of just typing Python, we're going to go into IPython, and that's going to give us a nice interactive environment to play with, where you'll be able to see a lot of what I'm doing, and ideally be able to follow along with that if you are so inclined. And so I'm just going to maximize this so that we've got the maximum area available. So to get things started, I'm going to do a couple of imports. I'm going to import NumPy as NP, and that will give me the NumPy library that we're going to use for the rest of the day. And I'm also going to do from matplotlib import pyplot as PLT. PLT. So those are a couple of sort of standard or traditional imports that we need to essentially access all of our packages. So NP is an alias for NumPy, so I don't have to keep typing that out. And then the same thing is PLT is an alias for this pyplot piece of matplotlib, which is where we interact with everything. So with that, then I'm going to do one of those magic commands in matplotlib, and I'm going to basically just set up matplotlib to go with the Qt library so that we're all set with that. And so I'm just now going to test something and see if a window comes up by doing plot.figure. Okay.
Eric, one more thing.
Okay.
Can you resize your terminal window so it's in from the left-hand side by about a third, because it overlaps with your icon, your camera. Yep. Perfect.
There we go.
That should work for most people. And can you click the hide button for your shared screen?
Okay.
Yep.
Great.
Awesome.
Thank you. So we've got a figure. And so if everything goes well in IPython, that's you should be able to type in those commands and get a figure up. If you're working in a Jupyter notebook, what you need to do is, instead of matplotlib qt, you're just going to need matplotlib inline, and you'll be set. So that's for Jupyter notebooks. And if you have issues, Alex can help you out on the chat line in the background. Okay, so what we're going to do right now is I'm going to actually pull up my slides, and I suppose I should slide this over so that you can see that. We're going to talk a little bit about matplotlib. And if you see this matplotlib object model, we're going to basically be creating what are called figures, which you see in the top half of that with the bolded figure title. And so the figure is the entire thing. Excuse me, both the x-axis, the y-axis, any data that's drawn on it, the title, the legends, all of that stuff. And so we're going to show you the basics of how to get a figure going with this. And if you start working with matplotlib, all of these pieces will start to make sense, because you can manipulate them individually and in great detail. And we're not going to get into all of those details today, but just focus on all the major pieces that are available, so you can pop something up on the screen, create a JPEG or a PNG file to save what you have if you want to, and play around with the figures and basically get started with it. So that said, I'm going to switch back to my IPython prompt, and we're going to set some stuff up so that we have some data from NumPy to basically start playing with and drawing. So I'm going to set up an array called P, grab NumPy, and a function called linear space. And we're going to create a linear space from 0 to 2 pi, so 2 times np.pi, and we're going to put 50 points in it. Okay, so if I type that all right, I now have something called t, which I can now look at. And you can see this array, and it's giving me row by row. It's starting at 0, and if you look at the bottom right-hand side, you see 6.28, which is 2 times pi, and there's actually 50 points in that. So that's our first piece. And now we're going to calculate some trigonometric functions on that. So we're going to make x be the sine of t. So again, we can look at x and see that that's ranging from 0 back to 0. Note this is scientific notation. That's what the e plus 00 on the end of all of these numbers means. And so that last number, which is e to the minus 16, is basically very, very close to 0, even if it's not quite 0. If I look at the size of x, we're going to see that it has 50 points as well. So just doing that sine of t, basically grabbed each element of t, applied the sign to it, and stored it in an array called x. We're going to do the same thing with the cosine, so that now we have a cosine function that ranges from 1 to 1 as expected with the cosine. So I'm going to pop my figure back up. In fact, don't really need to do that again, but just for completeness, we'll go ahead and pop that back up. And it's going to keep going behind the window, so I'll have to keep pulling it forward with this limited screen space. But see, now we have a blank canvas that we can draw on. And the way Matplotlib works is there's an active figure, and as we issue commands in this interactive mode, you're going to see all of our data being drawn on to that figure as we go forward. So first thing I'm going to do is plot x. So plt.plotx. We'll set that up. And so there's our sine wave. So a couple things to note about it. The y-axis that's ranging from -1 to 1 was automatically selected from the data. Matplotlib's smart enough to see, okay, that's the range of what's going on with the y-axis, so it sets that up for us. And then on the x-axis, note that it's going from 0 up to 50. And because we didn't provide it with data for the x-axis, it's basically looking at how many data points and saying, okay, data points starting at position 0 all the way up to 50, I'm going to draw them. So that if I want to now, I can create a new figure. So we'll just move that one up here. It'll pop behind plot.figure. That gives us a new canvas. So let's just show you all of those. So we've got now our two separate canvases. And when we plot our Y array on it, we will actually get both of those for us right there. Oops. So there's our cosine function and our sine function, just very simply there. And in fact, if we wanted to distinguish these on the current plot, we can very easily just put a title on and call this cosine. And so, again, pop that forward, and that's right there so that you can see all that. So getting something into Matplotlib is really straightforward. The hardest part is getting all the imports right and deciding inline or whether you want windows, depending on what environment you're in. But having it draw the data can be as straightforward as just run this plot.plt or plt.plot and then pass in an array of data from NumPy, and it will go and do one of these very straightforward plots for you. So,
hey, Eric?
Yes?
Could you do this first section from Jupyter to get everything? There's about half of the people who are using Jupyter.
Okay.
Could you start your Jupyter server and similar steps from Jupyter just to make sure everyone is on the same page?
That is a good idea. So I'm just going to start up my Jupyter server. Okay, and we'll just minimize that window. And we're just going to create a new notebook. Okay, so exactly the same stuff. We're going to do import NumPy as NP. We're going to import matplotlib, or excuse me, as NP from matplotlib, import pyplot as PLT. And so that's our basic imports, and then we can set up our linear space for T, 2 times np.py, get 50 points out of it. And so if we go ahead and I'm going to just run that and show you what that linear space looks like. So interactively, there's T, and we can go to the next cell. And
Eric,
yeah,
can you
my font bigger?
No, the font is fine. Click the view menu and hide a few things so you can use more vertical space.
Okay.
Toggle header. Yeah. And if you click on out, no, that's it. That's the best you can do.
Yeah.
Click on the margin. Yeah, double click there. Or once or twice. Yeah, in this hover place, it should hide the output. Yeah, okay. So people can see more of the code.
Okay.
And you'll need don't forget the %matplotlib magic.
Yes, thank you.
Yep.
Okay, so we'll set up X and Y, and that's run. I have not put anything out there, so we can look at, for instance, X and run it, and we'll get rid of that. And then we'll insert another cell. And so we'll set up the matplotlib. Matplotlib, we'll set this up as inline. And we'll create a figure. And we'll go ahead and plot X. So now if we run that, you can see that all goes up there. And that magic command is very important in getting matplotlib set up so that in this environment it knows not to try and pop up a window, which it can't in the browser, but instead to insert the image inline right there. So just to recapitulate, we went through the imports, ran through, creating our basic T array going from 0 to 2 pi, created 2 more arrays with sine and cosine. And then finally in matplotlib, we plotted that figure and just plotted x. So now if I insert a new cell, we will select this cell and insert a new cell below. There we go. And we can create a new figure right here. And we can basically plot y. And we will go ahead and put the title in and run it. And so you can see all of those pieces show up right there for you. So you can basically follow either path. And the one real difference is this piece right here, is that if you're in the Jupyter Notebook, you need the matplotlib inline. And if you're in IPython, it's the corresponding matplotlib Qt, which is right there. So depending on where you're more comfortable, you can follow along in either place. Okay. So let's play a little bit more with the plots. So we're going to set up some new data right here, just to show you that again. And I'm going to recycle my x variable. And this time we're going to make it run from 0 to 2 pi. And again, grab 50 points. And we're going to create 2 new functions. Y1 is going to be sine of x, and y2 is going to be sine of 2 times x. So before we get the sign, we're going to multiply each value in our x array by 2 and get a sign of 2x in this case. And so let's look at a couple of things here. One, let me get rid of my windows. I'm going to get a new window, plot.figure. So get that up and out of the way for the moment. And we're going to go ahead and plot y1. So this is exactly the same thing I did before, in that we're plotting our sine wave and we're getting ranges from 0 to 50 on the bottom. Now, if I want to change it so that I can plot x with y1, I'm going to just plot this on top so that you can see what happens on this. And you'll notice the second one is in orange. It's using x for the x value, so that's going to get compressed between 0 and 2 pi, so about 6.28 right there on top of each other. And we're using the same figure. And so what I want to do is actually make it so that we have the proper x values on the bottom rather than those positional arguments, which, just showing us how many points we have. So I'm going to clear my figure, plot.clf. So we're back to a blank slate, and I'm just going to go ahead and plot my x and y1 again. So now you'll see this time it's, again, the sine wave in blue, but the x-axis is running from 0 to 6, to essentially up to 2 pi, so that we've got now a proper plot of that sine wave with both the x and the y. So if I don't like blue, I can go play with this a little bit. So I use the same command, and I can go ahead and put in a formatting statement here, which is basically saying I want to plot a red dashed line with circles on the actual data points. And so you can see it goes on top. So I've got a red with the R, the dash is the line plot, and then the circles is the O. And so I've got to know those codings. And on your slide that corresponds with this section, slide 7, there are a couple of little tables there that show you the color codes and some of the symbol codes so that you can see what some of your options are. If I go ahead and clear this plot again, let's try another variation. So plot.clf. And if I go ahead and neglect to put the dash in, what happens? So now it's just a point plot where we're plotting the actual points, but not trying to draw any lines in between them. And if I don't like that symbol, I can go ahead and say, you know, I want to have plus signs, for example. And so now all of my points have a plus. And so you can go through and play around with all the symbols and see what you like best for whatever your display purposes are. So let's now, I've cleared the plot again. What I'm going to do is plot a couple of data sets on the same plot. So we're going to plot X and Y1, and we're going to make this a green line plot with circles. And then I can just put another comma and plot a second data set. We're going to have X on the X-axis again, but this time it's going to be Y2. And this time I'm going to make it a blue line plot with plus signs. And so I can basically, having these triplets of X, Y, and format, plot as many things on the same figure as I want and just overlay them on top of each other. So X and Y1 is green with the formatting was specified, and X and Y2 is this blue line, again, with the formatting we specified. Okay, and you can see that the period of the 2x, sine of 2x is basically twice that, or the frequency is twice that. If we want to make it so that our users can actually have a legend, we're going to provide a legend with a couple of titles. And notice this is a title with a list. So the square brackets right here are saying we want a list of titles, and basically the order I plotted them in is the order I want my titles in. So now I'm providing a list that has sine of x and sine of 2x in it. And there's our legend, and Matplotlib has automatically selected a nice free spot in the upper right-hand corner. You can go in and there's a way to tell it exactly where you want the legend, but it will do its best job to find a nice free spot and put the legend there for you. And so most of the time, unless you've got a very complex plot, Matplotlib does a nice job of figuring out exactly where things would go most conveniently. So again, just to recapitulate what we did, we generated data for our x-axis, then we got y-axis data with sine of x, sine of 2x, and then we can plot those in a variety of ways. And if you want to have an actual x-axis that represents your data, you need to include the x data in the plot. But if you don't want that, or you don't have it, it will provide an x-axis that gives you the positions that your y data was in and draw the line plot that way. So,
Eric?
Yes.
Just a quick thing for people following along in Jupyter. All the things that Eric just showed about doing plots and interactively adding features, adding lines, and adding legends. That code, if you're in a notebook, it has to be in the same cell. So if you want to add a legend, you have to go back in the cell where you created the figure, add the legend, call there, re-execute that cell. If you add a legend call in a separate cell, Jupyter doesn't know which plot you're talking about and then won't be able to add the legend.
Yeah, in Jupyter, the figures are tied to a specific cell, basically. Thank you. Okay, so that's a line plot. We can also do what's called a scatter plot very easily. So let's get some data for that all set up, and I'll just scroll up a bit. And this time we're going to specify a variable that says how many points we want. So we're going to call that capital N. And I'm going to create a new linear space. But instead of going from 0 to 2 pi, I'm going to go from 0 to 10 and make n. And if you want to, you can go look at that, verify exactly what's going on with your x variable. And I'm going to actually import a random number function so that we can add some noise to this to make the plot a little more interesting. So from the random package in NumPy, which is another great package to look into if you need a random number generators of various types. There's a lot of stuff there. We're going to use the rand function, and we're going to essentially create a noise array where we're going to get 50 random points, multiply them by 5, and essentially it looks like that. So you're likely to get something different in terms of those precise values on your machine, but essentially rand gives us numbers between 0 and 1, and we're just rescaling them from 0 to 5 so that we have 50 points with those random numbers in them. And we're going to now create our y data and basically take x, which ran nicely from 0 to 10, and this time we're going to add the noise in so that our y data is a little noisier than, well, a lot noisier than our x data. Okay, so let's take a look at this. We're going to create a scatter plot out of this, and I'm going to put in my x data, my y data, and we'll just get started with that. And so this is the basic scatter plot that shows up. And again, x is running from 0 to 10, and then y, depending on what the random numbers are in there, are fouling up the y data so that you actually get this noisy diagonal line across your screen. Okay, so with the scatter plot, we often want to visualize things by having our points be different sizes. So I'm going to show you how to do that. So to do that, we're going to create something called areas, and that's just an arbitrary name. And we're going to take our random number generator, and this time we're going to basically scale it by 100. So now we're going to have 50 areas that run from near 0 up to near 100. And if we go ahead and we do the same scatter, but specify a size argument, s equal to areas, we're going to get that. And so you can see how those dots are now of a variety of different sizes depending on where the random numbers hit on that. So you can do that. And then another way you might want to encode something for display is you might have each dot now represents something, and we're going to apply a different set of colors to it so that you can encode some more information there in terms of the colors of each of those circles. So we're going to go ahead and set up our colors as, again, some random numbers. Ideally, in whatever you're studying, you're not just generating random numbers, but actually making this meaningful. And we simply go ahead and take our scatter line, and we have C equals colors, so that now we can add that layer of information in. And so you can see we've got the same shape, different sizes, and now each dot has a different color coding on it so that you can have some interpretation of that. So what do the colors mean? Let's go ahead and add a color bar. So plot.color bar. And we have now, remember when we did the colors, it was just a random number. So it's ranging from 0 to 1. And that's what our color bar shows us. So the dark purple are close to 0, and the yellower it gets is close to 1, so that you're able then to apply data to that. Now, that's just a standard color bar. You could have any one of a large library of different color bars with different color schemes, so that you could associate something with something more intuitive. For instance, if I wanted the dot colors to represent a temperature, I might have a color bar ranging from blue to red, cold to hot, or something like that. And so there's a whole library of these color bars where you can create your own, so that you can color these however you want to make it meaningful to your problem domain. I want to put in a title.
Eric?
Yes?
Some questions from the chat. Can you explain again what the S keyword does? The S equals area.
Okay. So the best way to figure that out is there's a feature in IPython that also works in your Jupyter notebook, is you have plot.scatter, and then you put a question mark, and that will tell you about all the stuff that, what the scatter function does, plus all of the arguments that are available. And so if we grab that, I just scroll up so you can see, it's giving us what's called the function signature up here at the top, where you see signature in red. And there's all these different arguments that we can put in, most of which we're not going to talk about. But S is either a scalar, so it's a single number indicating the size in what are called points. And then, or we're providing an array that is essentially the same size as our data arrays, so that we can essentially set up a size for each of the dots. So all S is it stands for size, and we're able to pass something in that tells it how to size each of the dots it's going to plot in the scatter plot. And the same thing with C is the color, so that we can assign a color to each of the dots as we want. So there's a lot of complications in terms of if I want to specify the color as red, I could just say color equals R, I believe. So instead of passing in all the colors, I can say color equals R, and now they're all going to be red for me. And if I go ahead and restore that to the way it was, then it's using this colors array to assign an individual color to each dot. So same thing with the areas. If I make my areas big, let's just make them all 100. So now all the dots are the same size. They're bigger than the defaults. And if I put in my, my areas array, which is a range of sizes from near 0 to near 100, then I can control the size of each individual dot so that I can encode some attribute of my data in there so that I can see that plot and have the size be meaningful. Maybe it's a population of microbes in petri dishes at various points, or something like that that allows me to indicate in my scatter plot some meaningful information for me.
One more question. Is the colors array a combination of RGB color? How do you, so here your colors array is just numbers. How does it map to a color on screen?
Okay. Let's go ahead and see what the documentation tells us. So if we look at here on the top where it says CMap, that's a color map. And so my array of colors is just 0 to 1 that is basically going to the default color map in the system. And so I can specify which color map I want. I just happen to have used the default one that's available, that 0 to 1 maps into the color map. I can go ahead and specify a lot of, so I essentially was using that one to set things up. You can create a 2D array where the rows are RGB numbers and or RGBA numbers, so that you could have in our case, we had 50 points. So you could have a 2D array that had 50 rows with 3 numbers in each row and specify RGB values if you wanted to do that.
Okay, thanks, Eric.
Mm-hmm. Anything else?
One thing.
Okay.
There's been some requests to slow down a little bit. It's hard to keep track with the windows moving, and it's hard to get I understand being remote like this, not having the face of people and typing along. So just a little slower.
Okay.
Yeah.
I will try and slow down a bit.
And I think at this point, so what's your schedule? How do you want to, when do you want to take breaks?
I basically think what I plan to do is get through the matplotlib and schedule the exercise back to back with a break, so that people who want to spend more time on the exercise have plenty of time to do that, and people who quickly finish can go do a break right after that, and then it sort of gives everybody enough time to use their time how they want to, and it's best for them.
Okay. Okay.
Probably in about 15 minutes, we'll do the exercise and a break.
Okay. And people are asking where to find the code and if you can share what you've written. So far, Eric has mainly typed things that are from the slides. So I'm pasting in the chat here the link to the slides. So if you have enough screen space to keep the video and your editor and the slides all open, that will help.
Yeah. I'm trying to stick to the slides for that reason. so that now if you've got the slides, you've got most of the code, maybe missing a couple of little nuances when I put a little more detail in, but the basics are all in the slides.
Someone's asking, is an array a list? I believe, do you want to address that now or in a little bit once you get to NumPy?
We'll get it into NumPy, but no, an array is not a list. And we'll talk about the details of what that is and why in the more NumPy centered part of the tutorial, and what the relationship between the lists and arrays are. So
good. Thanks, Eric.
Okay. So we've talked about line plots. We've talked about scatter plots. Then there is another type of plot called an image plot. And again, we'll set up some data for this using our random number function. So we're going to set up E1, just get 100 random numbers. And E2 is going to be a bunch of random numbers again, this time multiplied by 2. E3 multiplied by 10, and then E4 is random multiplied by 100. So again, these all basically look the same. They're just scaled differently, and they'll have a different set of random numbers. But you've got essentially an array with 100 things in it that we're now going to use to create a plot. So what we're going to create here is a correlation matrix that will basically show how these different numbers are correlated with each other. And so the correlation matrix basically is going to line all of our data sets up against each other in a grid, showing how often the points in each of our data sets matches the other ones, how closely they match. And so we're passing in a list of arrays. So I'm just passing them in the order that I created them. So E1, E2, E3, and E4 are inside the list in the brackets. And then we're going to tell it to create this correlation matrix. And we can, again, take a look at it, see what's in there. And it essentially, if we look at, say, this top left one, this is E1 versus E1, line up all the points and see if you can draw a regression line through it. And for those of you who remember regression lines, when R squared is 1, everything absolutely matches with the other. And so everything's absolutely correlated. So all these ones down the diagonal, that's E2 versus E2, E3 versus E3, E4 versus E4. And then when we get over here, this is E2 versus E1, and things are not correlated anymore, which we sort of expect with this bunch of random numbers, that there's going to be a few things that are correlated with each other, but not a lot. And so that's what the data in the correlation matrix is showing us. And it's often easier to see what's going on if we plot this as an image. So this is generally just how to plot a matrix as an image. And so we're just going to put our correlation matrix in as the data. And this time we're going to select a particular color map, and we're going to use what's called the green-blue color map and show that, so that, again, if you look at the data, that diagonal, very strong correlation, but things that fall off the diagonal are not very well correlated with each other. And you just have to imagine that you've got E1, E2, E3, E4 as the coordinates across the top, and the same thing across the y-axis, and then you can see how they line up with each other. If I want to, I can also put on a color bar so that now I can see my correlations, so that on the top of this, everything that is that dark blue, the correlation is near 1, and everything that is down near the almost white is not very correlated at all. And then the green is maybe a little correlation, but really no strong correlations there. So your colors will probably show up to be, a little different, but you should see that same basic pattern on your system. Alex, do I have any questions on this one?
Yes. Someone's asking, why are the correlation values scaled between 0 and 1? That's a trick question.
That's a trick question. Oh, that's a good question, though. So let's see if you can answer it, Alex. Basically,
it's normalized by the sum of the points. Like, I haven't thought about this in a while, but it's somewhere in the computation of the correlation is divided by the sum of all the numbers, and the maximum sum, the sum of all the numbers divided by the sum of all the numbers, will give you a 1.
Yeah.
The
and
exercise is left to the reader. The point here is not so much about the correlation coefficient computation, but the fact that there's a NumPy function for it that can do that for you and that you can visualize it.
Yeah. And if you look at all those negative numbers, they're actually very close to 0. And so it's not like you're getting large negative numbers either. So for the most part, what you're seeing is that 0 to 1 correlation on that, and whether something's correlated or not. But now that 0 on the color bar does bump down just a little bit, but it's essentially no correlation up to full correlation is what we're showing.
Yep. Another question is, how can I learn more about color maps?
Okay.
How can I discover?
The best way is to type in matplotlib color map. And here's the color map reference. And there's a whole bunch of stuff there. Let me see if I can go ahead and put that in the chat. Oops, that didn't work. What did it copy?
No, it's good. It's there. It just takes a second.
Okay. Yeah. Okay. Yeah, I've not scrolled down all the way to the bottom. There we go. So
another thing, can you go in IPython?
Sure.
So if you know the name, what Eric showed you is that you can type the name, but you can also do plt.cm. So this is the dot, press period, and then the tab key on your keyboard. And this will autocomplete. This should work in Jupyter and in IPython. This will show you all of the names. So if you press tab once more, then it highlights one, and then you can use the arrows on your keyboard to navigate all the names. So if you have a vague memory of how something is called and you don't want to go look it up, the tab completion like this is a good way to discover more color maps.
Yeah, and lots more color maps.
Yes.
Yeah, and don't forget that this is sorted computer-wise. So all the ones that start with capital letters show up before the ones that show up with lowercase letters. So there's probably twice as many as you think that there are.
Yeah. Another question is, how can you save the figure?
That's a good question. There is on the figure itself, and it's really hard to see, but in the icons on the top, there's a little disk icon. You can go ahead and click on that, and it will ask you, what you want to do. But you can also do a plot.savefig and just give it a name, plot.jpg, for example, and it'll actually save that in wherever your current directory is. So if you do a magic %pwd, you'll see where that's actually saved. And so if I just go there, I have to go ahead and navigate. And what did I call it? Plot.jpg. It's right there. And open it through with Paint. And there it is.
So will this work in Jupyter as well?
The plot.savefig should definitely work in Jupyter.
Okay, thanks.
Okay, so let's now talk a little bit about putting multiple plots onto the same figure, because sometimes you don't want things overwriting each other and you've got more complex things that you want to do and have things display together. So I'm going to recreate my T linear space that we started out with. And again, 0 to 2 times np.pi, and put in 50 points.
Oh, actually, Eric.
Yeah.
One more thing. So can you go, this is a question from Dan about what the plt.cm command does. Can you combine line 64 where you do an imshow with using the plt.cm command that we discussed earlier?
So you mean like this?
Yes.
Which, I don't know. There's the green, blue. Let's do grays.
There we go. Thank you, Eric.
Sure. So yeah, changing your color map just allows you to pick a different color scheme very easily. And as we saw, there are lots and lots of them. And so you're likely to find one that's, fits your problem domain or what you're trying to show.
And can you talk a little bit more about tab completion? When it works and when it doesn't work?
So, if I start typing PL, no dots, it's basically going to, IPython's going to try and find all of the variable names and things that I've set up with, directories, all sorts of stuff. So I just type COR tab to get my correlation matrix. If I just type CO, it's going to give me all these things that maybe are right in terms of IPython commands, local directories, or variable names or commands of various sorts. And so I just type enough to select one, hit tab, or if I hit tab twice, then I can use my up and down arrows to basically navigate through the screen that's showing things for me. Now, when I have something like plot dot tab, it's going to assume everything starts with plt dot and then give me all sorts of options off of the plot object that I imported and what all is available to me for that. So it's mostly a matter of start typing something and hit tab and see what comes up. And if you play with it, you'll get familiar with it. And it's quite helpful in doing a lot of shortcuts on your typing. So
thanks.
Mm-hmm.
Thanks, Eric.
Okay. So again, we're going to recreate our T linear space. And I'm going to create X as NP sine of T and Y as NP cosine of T. So that's all there. And what we want to do now is, instead of just doing a regular plot like we've done, we're going to divide our plot into what are called subplots. So the subplot function will basically allow us to specify a number of rows. So I want 2 rows in my figure, and I'm only going to want 1 column. And then I'm going to make the first subplot be the active one as far as matplotlib is concerned. And those of you who are new to Python may have been told Python starts counting from 0. Well, matplotlib starts counting from 1. So my first subplot, that last number there, is actually number 1. So if I hit enter, I'm going to get this figure that shows up, and you can see that the top half, which is the first row, is active, and there's some x-axis and y-axis, a place for me to plot some data, but the lower half is empty because I have not made that one active and ready to put anything there. And we'll see how that goes. So if I want to put my x data now in my active subplot, I just plot x just like I do to a regular figure. And you can see now it's occupying the top half. And again, the x-axis, I didn't provide the x data or the t for that. So it's just ranging from 0 to 50. But the y-axis is going from -1 to 1. Now, to get the next subplot, it's plot.subplot. I'm going to again specify 2 rows, 1 column, but this time I want to make the second subplot be the active one. And so now you can see that that shows up right below that on the second row. And we're going to go ahead and put the y data there. The cosine data. So now we have the cosine and the sine on top and the cosine on the bottom lined up with each other so that you can see what's going on. Now I could do,
Eric?
Yes.
Question for you. How can you set the figure size if you're using subplot?
How can you set the figure size?
Is it an argument to subplot, or do you create the figure first?
Well, let's go check that out. I do not know the answer to that question.
I think, can you go down? So figure, the argument is called fig size. So I would typically create the figure first using the fig size argument and passing it a tuple of integers, but maybe this works here. That's going to be really, really big. Don't do that.
I don't know.
Like 16 by 10 is good. It's in inches.
It's in inches. Okay.
Yes, not in. Okay.
So you didn't like that. So you're going to want to do plot.figure. Fig size equals 4 by 4. So
yeah, so that's a tiny figure.
My tiny figure. And now if I do my subplot, in fact, while we're at it, let's just change this 1 row and 2 columns, and we'll make the first one active. So now there's 1 row, 2 columns, and we can see how we can mangle our X data. It's there, and we can now do the same sizing, but select number 2 as active and plot Y in that. So side by side, or over each other, but basic.
And then how would you label them? Which one is plot 1 and which one is plot 2? Would you give them a title?
We will get to that on another slide. And so let me follow the slides so that we'll show you how to do that in a moment.
Okay.
Okay. Okay, so now I want to show you how to create a histogram as our final plot type that we typically get people started with. So we're going to create a new set of random data. And we're going to just say data is equal to rand int. And I'm going to have 10,000 points, or up to 10,000, and then we're going to make it. Oops. Size equals, sorry. There we go. So we have this large data set that I'm not going to display for you, although it'll truncate things nicely, but it'll occupy an awful lot of real estate. And what we're going to do is sum up this data so that we can bin things for our histogram. So that's what X looks like. Again, lots of points getting summed up. And again, the code is in the slide, so you'll be able to go back and look at it. Or in fact, if you want to see all of that together, I can do this %history magic command and see what I've typed in. So essentially, these are the two things that are relevant right here. So we'll put that on top so you can see that. And what we're going to do now is go ahead and create our subplots, 2, 1, 1. And we're back to the regular size that I have set in my environment. And so 2 rows, 1 column, make the first one active. And now we're going to plot the histogram with the X data, and then we're going to tell it we want it to be red. So there's that histogram. And then we're going to select the next subplot. So plot.subplot, 2 rows, 1 column, make the second one active. So there it is, ready to go on the bottom. And then we're going to do a histogram and show you what the histogram looks like if we set the cumulative keyword argument to true. And so that's as we go through the histogram, it sums everything up so that we're going to get all of our data showing up to the right. So you've got a couple of different options on the histograms. So, we can go ahead and do this another way. And let me just show you how this works. So if you've got multiple data sets that you want to create histograms of, and I'm just going to repurpose X a couple of times, it'll actually show the histograms side by side. I'm using the same data here, so there's no difference between the size of the bars, but I can pass in a list of data elements. And so however many data sets are there, it'll plot in the histogram. So if I go ahead and do 3 of these, I'm going to get a bar for each one showing up for each of my bins in the histogram. And there's a lot of arguments on histogram. So again, if you look at hist, you can go ahead and control how the bins are set up, weighting things, all sorts of different arguments that you can look at the documentation, again, for figuring out what fits your problem domain the best in terms of what you want to show. And the documentation in Matplotlib is actually phenomenal in terms of the amount of stuff that they give you. Okay. Any questions on that, Alex?
So there were some people catching up with the size and random. Let me see. Does the true have to have a capital letter?
Absolutely. So true in Python is capital T, lowercase RUE. If I just type true without the capital letter, it doesn't know what it is. And if I type it all caps, it doesn't know what it is. False is the same way, capital F, and everything else lowercase.
Thank you. Someone was asking, can you normalize the y-axis for the histogram to go from 0 to 1?
I can certainly do that in the data, but is there an argument that allows you to normalize that?
There's a normed argument at the top. I think you skipped over it.
Oh, did I? Oops. Doesn't go back like I want it to.
It's normed
at the very bottom of the documentation. So normed, use the density keyword argument instead. So now we have to go back and figure out what density is. Well, let's see what it looks like. Let's just go plot histogram color density equals true. Or is that? Yep.
Yeah, that was it.
There we go. Although I'm not sure what.
There are questions about the axis keyword. I'm going to answer for Eric now. We're going to talk about this after the break, or Eric's going to talk about this after the break.
Yes, thank you. Okay, so let's talk about adding labels and legends and a couple of things that we can do on our plots. So I still have my T data set. And so I'm actually, now I can make the computation right here, pass the data set in, and we're going to call this label sine. And so as I'm plotting the data, I'm adding a label to it that is basically being held by matplotlib in the background in memory so that it knows what this blue line should be labeled. And we're going to go ahead now and plot our cosine on top of the same figure. Oops. And we're going to label it equal to cosine. And so the cosine is coming up in orange, just overwriting it. Now if I just do the legend, now if you remember the last time I had to pass in a list of my labels like this and make sure it was in the order I plotted things. This time, because I labeled each plot when I plotted it, I don't have to do that, and I can just get the legend. And notice that this time it shows up in the lower left-hand corner because it would have overwritten part of the plot in the upper right-hand corner this time. And so it's, like I said, matplotlib is very good about figuring out where to put the legend in a lot of cases. Okay. Let's go ahead and look at setting some titles on the X and Y axes. So again, we'll just create a basic plot. This time we're going to plot T and NP sine of T. So we have X and Y data this time. So there's where that is. And to plot something on the X label, I can just grab that and say I want that to be in radians. And you'll see this radians. Maybe if you squint, I don't know how that is turning up on your side, but it's using the default font. Let's plot the Y label. And that one is just going to be called amplitude. And this time, let's make the font size large. So there's a lot of keywords on that. So you can see amplitude is a little bigger. If I want to redo that, and let's just make this to be a 32-point font. See, we make that really big. See, now it's quite big. You can see it. I made it so big it's now cutting off of the figure. But you can use these keywords, large, small, let it do the default, or you can actually put in a numeric font size and play around with that. If you know how many points you want your font to be on that image. So a lot of ability to play with that. And then we can put a title on the figure, and we'll just call this sine of X. And so now that title's there up on the top. And again, you can play around with the font size. We'll make it 24. So you can get those titles all in the size you want. Matplotlib has reasonable defaults for setting things up, but sometimes you want to make them a little bigger or smaller, depending on your use case. Okay, so I'm going to jump back to the slides briefly and just talk about one more point. Here's my slides. And so we've gone through all of the stuff in the slides. Just want to make a point that when you're in interactive mode, we typically issue a plot.figure, and then we can watch our plot being made as you've seen. So in IPython, and then as Alex noted on a Jupyter notebook, you're trying to do everything within a single cell for that figure, because the figure is tied to that cell in the Jupyter Notebook. And then if you're running from a script, you're actually not going to see anything on this plot.figure until you run this plot.show command, and that's what's going to pop up the window in a script so that you can see what's going on. So you see the end result rather than this interactive, do a command, look at the figure, see what happened, do the next command, look at the figure, see what happened, and so on. When you're doing it as a script, it saves it all in the background, and then when you tell it to show it, it draws the whole thing all at once for you. Okay. So what I would like you to do now is we're going to go find where I've stashed all of this stuff. So find where or open your Jupyter Notebooks, or if you want to, you can actually do this from the scripts or IPython. But the easiest way is probably to go to your Jupyter Notebooks, go into your NumPy tutorial SciPy conference 2020, go into exercises, and then go into plotting. And there is a plotting.ipynb file. If you go in there, there's a nice exercise to go through and give you a chance to play around with some of the plotting and guide you through that and show you how that's set up. So let's allocate, say, let's resume at 11, because that'll give us a bit of a long break and give you a chance to look at the exercise and give everybody a chance to play around with that and finish it. And we'll be online if you run into any hurdles immediately for dealing with that. Does that sound good, Alex?
I suggest doing a little shorter, maybe like 20 minutes or something.
Okay. So
instead of 35. So right now it's 10:25 in Central. So that would be 10:45 or so.
Let's do 10:45 then.
So in about 20 minutes, we'll be both online. I think everyone needs a break here. Can you, so the exercise, just to be clear with everyone, it's called plotting. Many people are pasting the path in the chat. So it's in the exercises folder. The folder is called plotting and the file is called plotting.ipynb. If you're using the notebook, if you're using the Python file, it's called plotting.py. All right.
Okay. So we'll see you again about 10:45 then.
Yep. I think, Eric, the easiest way is just turn off your camera and to mute if you have to go away. And then to share your screen again when you come back. Actually, can you leave your screen on if you're not using your computer and put back the notebook that you, the terminal? Some people are asking questions about the code. So you can put it on screen. Actually, can you do a percent history and show like... Yeah, it's not the best thing, but that's what will show the most of what happened.
Mm-hmm.
Yes, Sheldon. We also need a break, so I'm going to be offline for 5 minutes, and then I'll be back to answer questions. And I believe Matt is still there, and Eric will eventually come back as well. So you're going to be alone for 5 minutes. Ooh, we'll be back. Hello, Eric.
Hello. Can you still hear me?
Yes.
Okay, good.
Before you walk through the solution, there's a good question that was asked during the break. Can you talk about the advantages and disadvantages of making plots in IPython versus Jupyter notebooks? Or like, what are the different sort of use cases for IPython and Jupyter?
Okay. The way I like to use IPython is when I'm exploring things and just trying to move back and forth, figure something out. For me, it's the place to start because all the tools are right there. I don't have to worry about cells. I don't have to worry about formatting things, making them look nice. I'm just in my little sandbox playing around and getting it all set up. When I go to a Jupyter notebook, I'm trying to present something to somebody in a little more organized fashion, where I might have some text cells with the notebook that describe what I'm going to do next, why, what's the rationale behind what's going on, and then basically, present a nice path through my explorations for somebody else so that they can see how I got from point A to point B without all the little detours that I inevitably took in IPython. And so I see that sort of the next level when now you're ready to talk to people and you want to show somebody else what's going on.
Okay. I'm going to add, so specifically about making plots in IPython versus Jupyter. So you can create the same plots, but if you're making them in IPython, like Eric said, it's great for discovery. But once you close the window, this plot doesn't exist anymore. So the nice thing about Jupyter is that it captures both the code that you're writing and also the output. So you get the code that generates the figure and the figure. And like Eric said, this is great when you are trying to communicate an idea with someone else so they can step through your thought process. The question that you're asking, the code that you wrote, the image, and then maybe some explanation as well.
Yeah, your cleaned up thought process. Your thought process after you've sort of edited it for public consumption.
Yep. There's a question that just came in. Can plots be in memory space for automation? Matthew, I'm going to okay. Can plots be in memory space for automated plot production? I assume, Matt, that what you mean is for like automatically saving figures for reports. Yes, they don't need to go on screen. They can just be automatically saved to disk with the plt.savefig function we talked about earlier. So that's definitely possible. And Chris is asking or making a comment that IPython seems a little like R, and that's true. Python and R both have a prompt, an interactive prompt that allow you to execute one line of code at a time or paste chunks of code, can generate plots. Yes. One more question, Eric, and then I think we can go back. What is the difference when you're in the terminal between typing Python and typing IPython?
Okay, so let me get a new terminal set up. And so I'm just going to activate a Python environment. So if I type Python, I'm basically in pure Python, and notice that I've got this prompt that's the 3 greater than signs. And so this, I can type any regular Python language thing in it, but I don't have any of the magic commands to interact with the environment and a lot of the nice things that IPython brings. So if I want to type in something Python, very quickly test it, it's fine, but I don't get a lot of the interactive abilities. Like, for instance, if I type A equals 5 in Python, and then I just type A, now I'm going to get that back out of it, but I don't have a way to look at, for instance, what variables I've set up and a lot of the magic stuff that we haven't talked about. IPython is definitely a better sandbox for playing around with. The other thing that's nice about the IPython is, that's my wrong window. That's the wrong one. I want that one. Is I get this. So for instance, that whos tells me everything I've set up already in IPython. Let me get rid of that window because that's making that a little confusing, I think. And so I can see what's going on in my environment, what I have already set up. I can do things like look at history and see all the commands that I've typed. And in fact, if I decide to type something in, I get this distinct, this is what I've typed in. It, in this case, is green, and this is what's coming out. In this case, it's red, so that I can easily, very visually distinguish things. And then there's a lot of color coding that goes on when I type an actual Python command in, so that I see how the IPython's interpreting it rather than it just being plain text. So it's a nicer environment. You can do a lot of the same things, but IPython has this additional stuff that makes interacting with Python really nice. Anything to add to that, Alex?
No, that's great.
Okay.
Just a reminder or something to do once the tutorial is over, people are asking about sharing the output of your history.
I actually just checked the first session of that on GitHub. There's a
wonderful
that now has a text file in it called session01_matplotlib. And I'll try and remember to do the next thing on the next session so that you can get all those commands and sort of grouped together by session, so you can figure those out.
Wonderful. Thank you on behalf of everyone.
Good luck sorting out my meandering path through IPython.
Yeah. There are some good questions that are sort of beyond the scope of the tutorial about EDM and R. I will type some things up in Slack in the tutorial NumPy channel because I think it's better if you talk about NumPy.
Okay.
So the floor is yours.
Okay. Thank you again, Alex. So let's go back to our Jupyter Notebook. And so you've been playing with plotting.ipynb. I'm going to look at the plotting solution. And so one of the nice things about our exercises is we give you the exercise, but we also give you an official solution. And I'm going to go through that quickly so that we can actually get to the main event, which is talking about NumPy, and make sure that we get a good solid foundation there. So just going to open up plotting solution. And as Alex said, Now it's going to have saved in it all of our input and output. So the idea of this exercise was you're supposed to come up with a plot, a figure in matplotlib terms that looks like this series of 3 different graphics on it. So how do we do that? And so we need a sine function with a blue solid line, a cosine function with red plus markers, wants us to play around with the extents. And then number 2, there's a sine function with grid lines, axis labels, and title. Again, play with the extents. Oops. Don't double click on things here unless you want to see the other way they look. And then an image with a color map, basically, again, playing with the extents, and then save it to a file. Then there's a bonus question that I'm going to leave as an exercise to you. There's a solution for the bonus that you can look at, but we're going to move on so that we can quickly get through all of this. I'm just going to comment about some of what happens here. So everything here in the solution is in a single cell. And so if I just go ahead and run this, I'll actually let it calculate, and you're going to see rather big images in the background for that. But let's just talk about some of the pieces. So this was all in this section set up in the exercise to set up your data. So here we have our X data, and then we have a sine and a cosine, essentially like we've been doing in the tutorial. But then we've also read in this JPEG as an image, and so it's being called IMG. So we're going to basically create a subplot with 2 rows and 2 columns, make the first one active, and on that we're going to plot the X data with the sine wave with a blue line, and then the X data with the cosine wave with the red plus marks. And then plot axis tight is basically going to pull everything in so that you get the axes really tight together. The second plot, we're essentially, again, 2 rows, 2 columns, choose the second position, which is going to be the top right-hand one in our 2x2 grid. And we're just going to plot the sine wave. We're going to put a grid on it, and then labels, titles, and then set the axis to tight. And then finally, in the third plot on the image plot, 2 rows, 2 columns, select number 3, which is the bottom left. And then we're essentially showing the image with the image show function extent. We're setting -10 to 10, -10 to 10. And then we're using this particular winter color code or color map, which allows you to see that. So create a tight layout so that it's essentially a very narrow boundary around it. And then we save the figure as myplots.fig, and that should have shown up in our myplots.png. Yep, right here. And we can pull that up with Paint and see what that looks like. So all of those plots together all in one place. And so matplotlib is mostly about getting your data set up and then breaking it into the plots and figuring out how to format things. So X data, Y data, format, X data, Y data, format on these line plots. Same thing here. we've chosen the default format, and then on the image plot, we're passing in the image and telling it how to display the colors in the image are the important things. Everything else is, labeling or titles or how to set up the axes and the layout. So solutions all there, easy to go back to. If you're interested in Matplotlib, I'd sit down and start playing with this in either IPython or Jupyter Notebook and seeing what other arguments are there and what happens when you change things around and play them. That's one of the great things about Python is it's cheap and forgiving to go ahead and make experiments. And that's where you're going to learn the most is by playing around with stuff. There's nothing you can hurt with these exercises. If you accidentally save something over, just download from GitHub again, and you'll be good to go. Any questions that anybody wants to ask specifically about the exercise? Okay. I'll rely on Alex in case there are any others going on in the background. Okay, so let's get to the main event. And I'm actually going to exit my iPad.
Sorry, Eric.
Yeah.
Sorry, I was muted. I had one question: how to save the image under a different format? For example, a vectorial format.
Under a what format?
Like vectorial, like PDF or EPS.
Well, for the most part, with plot.savefig, you just change that to like myplots.pdf. Mm-hmm. And it's very good at associating an extension on the file name with the format. The other thing you can do, and let me just plot.savefig ? I can go in and see this format keyword. I can go look for that, and basically here are the formats supported by most backends, and so I can specify it there. But the easiest way is just put .png or .ps or .eps, and it will just work as expected.
All right. Thank you, Eric.
Mm-hmm.
Someone was asking, what is the purpose of PLT that close with the string all? Which I think is not in this solution, but it will close all the figures that are open. So it doesn't do much in Jupyter, but if you're running it from Python or from an IPython, it will close all the figures before running the rest of the code, which is useful so you can be sure that the figures you look at are the most recent ones.
Yeah, so like I had a figure there. If I go back and now I do a plot, I don't know, T on it, it just overwrites my figure and I mess things up. But if I do a plot.close, so all like that, mm-hmm. It closes them. And then now when I plot my data, I've got a nice clean figure. So yeah, in the Jupyter Notebook, it doesn't do much, but it prevents you from doing what I do all the time, which is add extra plots to the same figure that was open and then having to go back, close it, and start again.
Got it. Thanks, Eric.
Thank you. So I'm going to go out so I get a clean history and go back into IPython so that we can see all of this again, and then I'll post this history for the next session there. So I'm going to import NumPy as NP so that now it's all available. And so first, I want to talk about how we set up an array, and I'm going to set up first a list, and we'll just talk a little bit about Python lists at the beginning so that we can address that question. Is an array a list, and what's the difference? So here I have just a plain Python list. So if I do type of L, it's just a list, and it's simply a bunch of numbers that are there, a bunch of integers, 0, 1, 2, and 3. Now, in Python, I can actually put anything I want into a list. And so, again, L2 is a list. Python doesn't care that I put stuff in, and one's a list of integers, another is a list of strings that are just a single character each. And in fact, Python allows me to do some crazy stuff like mix and match these however I want. And as long as I'm consistent on my notation, it does not really care what I put in the list. In fact, I can go ahead and make a list that is a list of lists and go to all sorts of different levels of contortion to get things into it. When we get into the NumPy array world, a lot of this goes out the window in that NumPy really wants you to always put the same type of stuff into your array. Now, we're now thinking of primarily scientific data where you've got, say a three-dimensional space where you're taking measurements of something and everything that's going into that array is the same type of data, and you actually want it to enforce that data type. And so the list is super flexible, but it's a little dangerous to use. And so the arrays enforce the data type so that we make sure that everything going into the array is the same sort of thing. The other thing that happens is like L4, I've got lists embedded in my list, and that becomes a little unwieldy. And how do I access things? And NumPy gives us a way to access things in multiple dimensions in a very natural way that we'll see later on as we go through it. And then the third major thing about NumPy and why we would want to use that rather than lists is it is a heck of a lot faster. It can be 100 times faster than a Python list in terms of processing because of the way it's written. And we can do our math operations very easily with it. So when we were doing matplotlib, you saw me create these arrays of 50 points and then just do one function call to get the sign of all those 50 points and not have to write any loops to go through the list and do all sorts of stuff for that, because NumPy is built for very efficiently processing arrays. It's very fast. And again, it's something that is what you could call type safe, where it's not going to let us put the wrong kind of stuff in the array. Now, we can still make mistakes, but it's not going to let us mix things up willy-nilly like we can with the Python list. And sometimes for good reasons, we want to do that. But in a NumPy array, we're typically doing mathematical operations, scientific processing, and we're wanting things to be essentially homogeneous and have a guarantee that that is the case. So all that said, the way I'm going to initialize an array is typically with a list or a function that can generate something for me. So it's very convenient in Python to create a list, and then when I want to turn it into an array, I call nparray and pass the list in, and now I have an array. And you can see when I display it in IPython or a Jupyter Notebook, it's telling me it's an array. And in fact, if I go and look at the type of this, it's a NumPy ND array as opposed to the type of L, which was a list. And it's just giving me the square brackets, which tell me that's a Python list. here we have this full thing spelled out so that we can see what's going on. Okay. So once I have it into an array, there's a bunch of attributes on the array that I can now look at to see what's going on the inside. So if I want to find out what data type that array is set up for, I just call a.datatype, and it will tell me that in my case, it's a 32-bit integer that is the data type. Some of you who are on Mac or Linux, it may show up as int64. That's okay. That's just telling you how much it's set up for on your particular system. I can look at my array and ask it how many dimensions are in the array. I happen to have set up a one-dimensional array. So, not very interesting. It's just a vector, but with NumPy, I could set up a 20-dimensional array if I wanted to, if I had that many dimensions of features that I'm looking at. And then finally, we can look at the shape of the array, and it's a one-dimensional array. So it's giving us what Python calls a tuple, and this is a one-dimensional tuple and how it displays it. So it's just 4 elements in this array that are there. Now, if I go back to looking at the list, so we have list, it's very easy for me to append another number to my list and add something to it so that I append the 5. I cannot go ahead and do that in a NumPy array. Once I set it up, its size, the number of slots that are available for me to use are fixed. And it's more like programming languages that you may have seen, C or Fortran or Java, where you have to specify the size of your array. And when I set up my original array, so let me get that window out of the way. So right there, by sending in a list with 4 elements, I basically told NumPy that I want this to be a one-dimensional array with 4 elements, and that's all the space that was allocated for it. So one thing arrays force you to do is to plan for how big of an array you actually want to have, because short of copying the array into a new space, you're not going to be able to just append stuff to it like you can with a Python list. Okay. Let's see. So we talked about shape. Let's look at item size. So this is another attribute on the array, and it's telling me that for each element of the array, I'm using 4 bytes. And so if you remember, my D type is a 32-bit integer. So each byte has 8 bits. So it's telling me that there are a total of 4 bytes for each cell in the array. And I can get out the total size of the array, which is 16. So for a small array, a lot of this stuff is probably not all that relevant. But what if you had a 1 million or billion element array that you're trying to load into memory and you're blowing out the memory on your laptop or your workstation? So it becomes very important to be cognizant of these attributes and knowing how big your array is going to be and thinking about that if you're dealing with very large data sets, which we often are in the science world. Okay, so those are basic attributes to arrays. So let's see some of the things that we can do with them that makes them nice. So I'm going to create 2 arrays here. And we're going to create this one, which we're going to call A, and I'm going to call NP array of B, and 2, 3, 4, and 5. So just have those two arrays that are now available to us. And the nice thing about NumPy is I can go ahead and add A and B, and you'll notice that it's doing an element-wise add. So this, in A we have 1, in B we have 2, and in my output I have 3. A we have 2, B we have 3, and in that same position in the output I have 5, and so on. So it's doing an element by element addition. We can do the same thing with multiplication. And in fact, any of the standard mathematical operations, we can do that, and we can even do exponentiation and raise A to the B and get answers out of all of these queries. So very simple way to essentially now start processing our arrays arithmetically and not having, again, to write loops or worry about making sure that you have the same position matched up in each array. NumPy does that for us. Okay.
All right, Eric.
Yes.
Some questions and comments for you. So your video looks good on my side. Some people seem to have some issues. Just a reminder to people that in the lower left of the window, there's a little gray text that says "Get audio video help." If you go down there, you'll be able to change the technology used for the audio and change the resolution of the video. I understand that if you turn the resolution down to like 360p, it'd be very hard to read the text, but there's nothing we can control on our side. It seems to be something about the internet. So sorry about that. Hopefully it'll settle soon. The other thing is someone was asking, so at the top on input 23, someone was asking why is there a 4 and some people have an 8? Do you have information on this for the item size?
So if I look at D type, if you have item size of 4, your D type should have been int32. If you have D type of int64, and I'll just create a new array to show you that. 3, and I'll set up my D type is equal to int64. So now t.dtype is int64 and t.item size is 8. So it's basically telling me how many bytes I need to allocate to store the particular data type that is associated with this array. So if you're on a Mac or Linux, it's typically int64. If you're on Windows, integers are by default typically going to be installed or stored as int32s. So 4-byte integers as opposed to 8-byte integers. But
yeah,
you can
so it'll be platform dependent.
What was that, Alex?
The default will depend on the platform, but yes, like you said, you can always control it yourself by specifying the D-type argument. Sorry. Then someone was asking why sometimes you see D-type and sometimes you don't see D-type, like in the output. So like on line 30, there is no D-type, and on line 31, there's a D-type.
That's a good question. I do not know the answer to that.
No, me neither. So usually it's because it's going to show you the D-type if it's not the default. But in this case, both of them should be int32. So I'm not sure.
Yeah, I'm not sure why the exponentiation resulted in telling you exactly what D type it is. But as Alex said, it's usually if it's warning you that you're not the default type for your platform.
Yep. And one more question, and then I'll let you go back. Let me check the box. Is there something smaller than 4 bytes, for example, to store indicator variables?
Yes. So there's a whole bunch of D types, and I'm not sure where to get that in documentation.
I don't think they'll be there. There's I think the online documentation at numpy.org will be the best place. I will paste the link. You don't have to go there.
Thank you.
But one to use is uint8. So that will be an unsigned 8-bit integer.
So like that. And so if you wanted to do something that ranges from 0 to 255, that would give you 1 byte and no sign on it. And you could do things that way. Got
it. Thanks, Eric. And I'll paste a link to the D types article from the documentation.
Thank you. Okay. So you saw how, just that example right there, you can basically create an NP array out of a list. If you have a list, that's great. But sometimes we want to create something that is a range of values without having to type them all in. And so I can create an array range. So a range, note that there's only 1 R. You'll probably see me type it with 2 R's a few times and call it a range. But we can basically put this in, and this will create a range from 0 up to, but not including 11. And notice the dot after the 11, we've got floating point values here. There's a similar function called range in Python that is restricted to integers, but in NumPy, we can actually use them with both integers and floating point values. So once I have this array, I can actually now go ahead and start playing with it mathematically. So one thing I'm going to do is I'm going to create a scalar value. So we're going to just say 2 times np.pi, and we're going to divide it by 10. So now it's 1/10 of 2 pi. And if I take my x array and I multiply it by the scalar, it's going to multiply that scalar through each element and create an array that's now from 0 up to 2 pi, because my x was actually going from 0 up to 10 inclusive, so that's all now set up for me. I can even do things like, now x here, I'm not changing it, I'm just getting a value back. I can do what's called in-place operations and say x equals x times c. And so now x itself is changed. And in fact, there's a shortcut for this where I can do x times equals c, and we'll just go ahead and mangle x further and just add in another, or multiply in another value of c, so that I'm able to either do x equals x divided by c, get things back, or I could even do x divided equals c. Those two forms are essentially equivalent. It's just that we often want to do a mathematical operation on an array and sort back in the array. And so this is simply a shortcut that allows us to do the do the math and store it in place in one command. Then finally, we'll go ahead and grab the sign of our x. And again, the sign function is going to be applied element by element across all of x so that we can not have to write any loops. NumPy is going to do all of that for us in the background. Okay. So after we've got these arrays, so we've talked a couple of ways of generating them with this range function, with lists. You saw the linear space earlier in matplotlib. So now that we have an array, what do we do with it? Basically, we can start indexing the array much as we can index a list in Python, and it starts counting at 0. So a of 0 is 1, a of 1 is 2, and so on, so that we can march through our array, specify the index of the element we want to see, and return that back to us. And I'm just going to get rid of that window. Okay. I can not only retrieve an element, I can actually set an element and say I want a of 0 to be 10. And so now I've replaced the 1 that was there originally and put a 10 in place. Notice that the D type is unchanged here. And in fact, if I go ahead and try and assign a floating point value to it, it's saying, sorry, you specified this as an integer, you gave me a floating point, and so I'm going to truncate this and just put the integer portion of that floating point value into the array. So probably should choose a better example, 12.6, and now if I look at A, there's 12 in there instead of the original 10. So you've got to, NumPy is flexible about, okay, I can use floating point values to assign, but because it's an integer array, you need to know that it's going to truncate it for you. In fact, there's a function that allows me to fill my entire array with a single value. And so I can put a floating point value in, I can put an integer value, and because A is an integer, it's truncating that -48 to just -4 and fills the entire array with -4s. So indexing, we can get values out, put values in, or this fill function, we can fill the entire array to set it up with whatever values we want in that array originally. Okay, so we've talked about the one-dimensional case. Let's go ahead and take a look at a two-dimensional case, since that is something you'll very likely run into. And so I'm going to set up my A array again, but to set it up, I'm going to pass a list of lists into my NP array function and basically pass in each row of data as I want to see it. So there's my end of my second list. I'm going to end the outer list loop, and you can see that IPython nicely highlights those for us to show how things are matching, and put the parentheses on for the np.array. And so now A is a two-dimensional array with 2 rows in it. So another nice thing about the interface is it's going to show me row by row and line it up so that I can get a visual representation that's actually useful for me to see what that array looks like. So we can go look at our attributes again. So the shape is 2 rows by 4 columns. So 1, 2 rows, and then you can see how each of the 4 columns line up. I can't do that with the mouse. So 0 and 10 are the first column, 1 and 11 are the next column, and so on. So that tuple tells me the actual shape of the array. If I look at the size of the array, there's a total of 8 cells in the array. So the tuple multiplied out gives me 8. And in fact, if I get the number of dimensions, I'm going to go ahead and see the number of dimensions on the array. Okay. Notice this shape is a 2 by 4. This is dimension 0 or axis 0 in NumPy terms. So we're going to talk more about the axis. Just want to introduce it to you. And the 4 is in the 1 position of the tuple, and so that is axis 1 in NumPy terms. So if you're ever trying to figure out which axis you're looking at on a multi-dimensional array, you get the shape, and then axis 0, axis 1 will tell you what's happening on each axis. Okay, so let's look at A again. And just like we can go ahead and index a single dimensional array, we can index a 2-dimensional array. And I'm going to pull out index of 1, 3. So that 1 is going to specify the row, which is right here, since we're counting 0 and then 1. And then the 3 specifies the column, so 0, 1, 2, 3. And so I'm going to get the intersection between the 2. And so unless I've misspoken, we should get a 13 out of that result. And there we go. So that I'm specifying rows and columns, just like the shape is rows and then columns, the indexes are going to be rows and columns. Then, just like in the 1-dimensional case, I can change something in the array by simply doing the indexing and then assigning a number to it with the equal sign. So there we've changed the 13 to a -1 by the position in the array. Then inevitably somebody will ask, well, this is a 2-dimensional array. What happens if I don't give it both dimensions in the index? And it'll basically pull out the row, and that's because my shape, the rows are defined in position 0. I'm putting the index in position 0, and so it's going to interpret that as give me the whole row and all of the columns. So I get basically that entire row with that indexing scheme. Okay. Alex, do we have any questions that we should jump into right now?
Well, it seems you've been doing really well because either people answer their own questions or they don't ask them. So we're good. Okay.
Sounds good. So if you remember slicing from your Python lists, we're able to slice in NumPy arrays as well. So let's set up a new array to play with slicing. 10, 11, 12, 13, and 14. And again, we're on slide 23 if you're trying to follow the slides. So we're back to the 1-dimensional case so that we can look at our slicing. And just like with Python lists, I can use this slice notation of saying, I want to start at index 1, so 0 and 1, and I want to go all the way up to index 3, but not include it. And so I'm going to with that slice, pull out the 11 and the 12. So because it's more than one element, it's going to give me an array back with just the elements that I've requested in it. Now, you may remember from your Python lists that we actually have two sets of indices on a list. So we've got the normal ones where we start with 0, 1, 2, 3, and 4, but we can also count from the end where this is index -1, -2, -3, -4, -5. And there's a nice graphic showing you that in the slide that you can refer to. But we can count from the beginning with the positive indices, or we can count from the end of our array with the negative indices, because sometimes it's more convenient to work from the end. And so I can say, I want A to start at index 1, but actually go up to, but not including 2 elements from the end. So again, 0 and 1 is there, and then -1 and -2. So we're going to do the same slice, but this time we're going to slice the upper bound from the end of the list. And you can mix and match these as you want. It can be a little confusing to do some of this, where I'm going to start from 4 from the end, but then end 3 from the beginning. And that's that third setup in terms of the way we can do this kind of slicing. So a lot of flexibility in terms of doing things from the end. Quite often you'll see, go up to the last element or the last but 2, and that's where you'll see the typical end indices.
Eric?
Now, yes.
Just to clarify one thing, Jack is asking whether some indices start from 0 and the arrays start with 1. So can you clarify, is NumPy like Python 0 based?
Yes. We're going to start counting from 0 on the forward indexes and counting from -1 on the ones from the end of the array. It's just like a Python list in terms of the way indexing works.
Okay. And the other one is a square bracket, comma 0 valid syntax?
Well, let's go ahead and test that. No, it's not.
Okay, so
if you're trying to just grab the 0 column, that question's perfect timing, that we use a colon as a placeholder, as in this case, go from the beginning to the end. So grab all the rows and then just give me the 0 column, and we're not in a 2-dimensional case, so it's not going to work there. But
yeah, Eric will get there in just a minute.
Yeah. But yeah. So let's go back to our A. And
one more thing, Eric, you don't have to do that now, but is it tricky to change the background color to white and the text to black?
Apparently,
it's surprisingly tricky.
IPython.
It might need to restart. So, okay, we're at the break. If you could give that a try.
The next break.
Okay, thank you.
Mm-hmm. Okay, so here we have our A array that we've been playing with. And so if we want to grab everything from the beginning and go up to index 3, we can basically start at the beginning point in the array and go all the way up to 3 not inclusive. So all the way up to 3 not inclusive. So that should give us that. That's the same as specifying 0 to 3, but this shorthand basically just says go from the beginning. And I can do that on the other end, where I'm going to say go from -2 to the end of my array. So -1, -2. And so it's going to grab that and go to the end. And so that'll give us 13 and 14. And then there, finally, just like we can in Python lists, we can specify a step size. And we can say something like, let's go from the beginning all the way to the end and just grab every other element. So let me just space this out so that essentially from the beginning to the end, because we're not specifying anything, and then slicing. That'll probably not work. It actually does. It doesn't care about spaces, but you'll see it typically from beginning to end like that to grab everything. And then that last element is telling how many times to jump. So by 3s, we can do that, or by 1s, give us the default, which is step by 1. Okay. Let's go ahead and set up well, actually, let's go to the slides for this one, since we have a nice picture that will take me a little time to recreate. And I scrolled too far. Introducing arrays. There we go. There we go. Okay, here we go. So in this example, we're going to use the arrays on the right-hand side, and the text is color-coded on the left to fit the array. So we've called the array 3 as usual, and so this first index is a row. It's saying grab row 0, so I'm grabbing all of these elements on the top row, and then I'm saying, but only go from column 3 up through column 5, not including the 5, so that's just going to pull out the orange 3 and 4 right there. So here's the two-dimensional case where I'm just pulling out a couple of elements here. In the blue case, we have, we're specifying from row 4 up to the end. So that's all of these rows, the 2 bottom rows here. And then I'm also going to specify columns 4 to the end. And so that simply selects the blue stuff out of the colored array. Then in the red section, I'm saying, okay, I only want to grab column 2, and so I have to specify that on the rows, I want to go all the way from the beginning to the end, and then for the columns, I'm simply specifying I want column 2, and that pulls out the red section for me. And then finally, in the highlighted, sort of the outlined blue sections, we can do what's called striding. Alex, are you saying something?
Yes, sorry, my microphone was far away. Can you try to zoom in a little bit to make the text bigger?
Okay.
And then once you're done, have some questions from people.
Okay. So we can also do this in a strided way, in that on the rows, we're going to start with row 2. So this row, And we're going to go all the way to the end, but include only every other row. So we're basically going to pull out row 2 and row 4 right there. And then in the columns side of things, we're going to go from beginning to end. So let's select all the columns, but only grab every other one. So it's going to select column 0, column 2, column 4, and our result is we're going to pick out the 20, 22, 24, 40, 42, and 44. Okay, so I have some questions. Let's.
Yes. Andrew's asking, why does A square bracket 0 colon 3 not have 4 elements? Right. So if you're making a slice, if you do A colon 3, why only 3 elements come out of this and not 4?
So are we talking about here?
Yeah.
So we're just doing A colon 3?
Yeah, or 0 colon 3.
Okay. So let's go back to the slide. And let's see if I've got a good picture. Okay, this is good enough. So here's my indexing on top here. So in this section right here, we're talking about going from 0 all the way up to 3. And as it notes in the slide on slicing, we start with 0 and we go all the way up to 3, but we don't include it in the way slicing is set up. It works the same in Python on lists. You're not including the upper index. There's some mathematical reasons why we do this, but if you're familiar with math notation, we're going square bracket 0 up to 3, and then parentheses is what in math notation we're saying is, we're going over this range, but don't include the upper bound. And a decision was made in Python that that's the way it's going to be, basically because I can now take my upper bound, subtract the lower bound from it, and figure out how many elements I'm going to get out of that. So 3 minus 0 is 3. And when I look at that result, I'm getting 3 elements out of it, not 4 elements. And that's sort of why the decision was made, but it's simply the way it works in Python and by extension in NumPy arrays. You have to remember that the lower bound is included, but the upper bound we go up to, but not including that one. Anything to add?
Wonderful.
To that, Alex?
No, I think that's good.
Okay.
Thank you. Yep, that's all. You can keep going.
Okay. So let's go ahead back to another array. Let's see what A looks like. Let's match the slide again. So we have A, and if we grab the last 2 elements, so we go from -2 to the end, we're going to grab 2 pieces there. And basically, with this slice of 2 pieces, we can essentially go ahead and put whatever in to that as long as it matches in size. So I've changed A now and changed more than one element of the array at a time by passing a Python list in that has the right data types, so integers in our case, so that now it fills the space that I specified with from -2 to the end. So 2 elements were pulled out of that index, we can put 2 elements back in. And in fact, if we want to, we can do the same thing with the scalar, with the caveat that what's going to happen is that we've pulled 2 elements out, we're putting in a scalar, and it's going to basically fill each element with that scalar value. If I try and do this with something that doesn't match in size, I'm going to get an error out of the system that says, hey, you gave me something with size 3, but there are only 2 slots open that you specified you want to put it into. It doesn't fit, so you're going to have to try again, and it won't make that change for you. And so you can do these slices and insert values in just like you can to a single index. That's simply a bit of the way that NumPy works. So let's give you a chance to play with that. And let me find the give it a try slide. So what you're going to do is go ahead and type in that command and then figure out how to do the slices to pull out the red elements, the blue elements, and the yellow elements so that you can do that. And we'll give you a couple of minutes to play with that. So at say 11:54 Central Time, we'll come back and hopefully everybody's had a chance to play with it, and we'll go through the solution and talk through that.
Can you experiment on the side without hiding the image with changing the color of your terminal?
Yeah. Just give it another one.
Oh, there we go.
Well, of course, your color. Since I guess I've changed all the defaults.
Can you resize a little bit, not to hide the square?
Yeah.
The cube.
And
whoa,
color.
That's worse.
Properties, colors, screen text. I swear it shows black. Why is that? So screen background is that, screen text.
What's pop-up text?
I know, but
you'll need a new terminal.
Yeah, but I swear no, that's all in yellow.
And if you start IPython?
Permanently mangled my
Is it because it's an invalid command and it'll change color?
Okay. It's doing some sort of syntax highlighting, so let's just see what IPython looks like. So there's IPython. Okay. So does that look better to you?
Can you move it up a little bit? You're hiding the...
I'm hiding it.
your photo, your icon. Move the bottom up, like yeah. Can you slice A? Or like just the syntax with square brackets? Yes, that is an improvement. I'm sure everyone will be happy. Cool.
Okay.
Thanks, Eric.
Mm-hmm. Okay, hopefully everybody's had a chance. I'm gonna see if I can run this where we can see it, since Alex made me redraw it anyway. So, first thing I'm gonna do is I'm gonna do NP arrange, and I just wanna point out something. So I'm creating a range of numbers going from 0 up to 25, but oops, import NumPy as NP in this window. Okay, so if we look at A, it's just a one-dimensional thing. If we do NP arrange dot reshape 5 by 5, then we're basically saying take those 25 elements that we created and make them into a two-dimensional array like in the picture. So let's focus on the yellow slice, since it's actually the easiest one to do. And so the easiest way to get this in my mind is it's a row. So it's a single row and it's just one from the end. And so if I just do A of -1, I'm going to be able to grab it. If I wanted to count the other way, so from the beginning, it's just the row at index 4. So those are equivalent, just where am I counting from? And then if I really wanted to, I could actually specify just the Y or the column information by putting a single colon that says go from beginning to end using the default step. So all of those are equivalent in that they grab the same bit of our two-dimensional array and give it back to us. The red pieces are similar, but this time we have to grab all the rows, and so I'm going to specify all the rows by saying going from beginning to end, and then I can specify a starting point, which the first red column is at 1. I can go to the end, but step by 2, so that I just grab every other one starting from 1. So that's the most straightforward way of doing that. And now the blue stuff, where we're going to have to deal with steps in both areas and potentially starting points. So we're going to focus on rows first. We're going to start with row 1, go up to the end, stepping by 2. And in columns, we're going to start with row 0. I'm going to go up to the end. It's going to be a mistake, but we're going to step by 2. We'll see what happens. And we're going to get, the 9 and 19 extra because I wanted to stop before the end. And so the question is, how do I do that? And so we can actually go up to column 3, which is just right after the last column in blue. And that should give us the results we want on that. So Slicing, if you've got a regular pattern, is extremely powerful, very useful, but requires you to have a pattern. So we will next talk about one item, and then we'll talk about what's called fancy indexing, which allows us to basically pull anything out of the array that we want to pull out.
I have some question.
Okay.
In the chat. Can you show again the solution for the red color?
Okay, so the red color, the first thing I notice is they extend on all the rows. So since I have to specify the row index first, I'm going to say all the rows, which is just a colon from beginning to end. Then on the columns, I'm going to specify, we're going to start at column 1, go all the way to the end. So I'm going to leave that as a blank, but I'm going to grab every other one. So step by 2. So I'm going to grab column 1, 3, 5, 7, 9, and wherever it ends, it ends. In this case, it ends at 5. So so it'll just grab those 2 for me.
And then can you walk us through again the solution for blue?
Okay. So again, blue, focus on the rows first. We're going to start in row 1, which is where the 5 and the 7 are. We're going to go all the way to the end, but we want to grab every other row. And so if I just do that first half, you'll see I'm grabbing each row that I want. So now that I've got that, I can go back, put a comma in, and specify now the red columns, where I want to start at 3, go up to 4, and step by 2. And that, oops. Yeah. Oh, no, yep. I'm looking at the wrong stuff again. Sorry.
Okay, yes.
There we go. That's a little better.
Okay.
So the blue stuff, we start on column 0, not column 1.
And one more question, not completely related to this exercise, but can you say a few words about the benefits or the use cases where you would like to start slicing from the end of an array with the negative indices?
Sometimes it's just convenient to count from the end rather than from the beginning. I
can give you one if you want.
Okay, go ahead.
So for this particular exercise, when you want to get the yellow, it depends on how you think about your data. If you think of your data, I want row label 4, then you'll do a square bracket 4. So that makes sense. But if you're thinking in terms of your data as I want the last row of this 2-dimensional array, then -1 is always the last row, whether you have 2 rows or 5,000 rows. So if you're thinking in terms of thinking in terms of 0 is from the beginning, so from the top, from the left, and the negative numbers is thinking from the relative to the end, so from the bottom or from the right.
And they're equivalent. It's just how do you think about your data for whatever reason? Say you have a time series and you want the last thing that was collected. And so rather than figuring out which row number the last thing that was collected happens to be on, you can just say, give me the last one. And that's what the -1 does.
Cool. Thanks, Eric.
Mm-hmm. Okay. So I'm going to use the slide for this one to get started. Or not this one. Let's go back to IPython and put Alex's favorite color one in there. So we're going to create a new array. And so just a simple 5-element array there. And we can go ahead and create a slice from 2 to 4 to pull out a couple of elements. And in fact, I can say, I want those elements, instead of giving them back to me on the screen, I'm going to say grab 2 to 4 and put that in B. So now B is all set up and very nice. And now I can go play with B and assign a value of 10 at index 0. So I go ahead and I look at B, and sure enough, it's changed. But now I go back and look at A, and notice right here, it's also changed. So when I set up this slice, I have what is a view of A rather than a copy of A. And so B and A both happen to point to, or the B points to something in the middle of A. And if I change B, I'm going to change that something in the middle of A. And so I have to be aware of that behavior of NumPy. Otherwise, you're going to run into problems where you're just not going to understand what's going on with that, because B is a view, and what I do to B, change 1 to 33, happens to A. And if I grab A and change what's in position 2 to minus 99, it's going to happen to B, because they're linked to the same underlying memory locations. And so anything I do to one affects the pieces that the other can see. If I don't want this to happen, I have to create a copy of the array. So if I slice A from 2 to 4 again, we're going to get these values. So now I'm going to do C equals A 2 to 4 on copy. And so now C is a separate copy of this. And I go ahead and set C of 0 equals to 1,000. And A is intact and B is intact. And that was done by doing the copy. Now, copies on very large data sets are going to occupy potentially another large amount of data. And so now you do copies judiciously because you know that's what you want to do. By default, we're going to have this behavior where that B slice is a view into A. And so we're not copying things, we're not moving things around. It's very fast. It's very direct. We're using the same basic underlying memory, but it can be dangerous if you do not realize that A and B are still linked to each other, still pointing to common memory locations, and therefore changes you make to B will affect A, and changes to A in certain positions will affect B. If you use the copy method, when you're doing your slice, you get a new independent array that's not linked to A. And so you can now operate on C separately from A without worrying about making changes. So it's a very important thing to make sure you figure out very early on in dealing with NumPy, because if you don't, there will be mysterious problems that you run into in the future and they'll be a little hard to explain until you realize that this is how it works. Okay. Let's talk now about fancy indexing. So how do you get something that doesn't have a nice mathematical pattern out of the system? Sometimes you want to create a mask so you can pull out elements based on, is this an odd or an even number, or, greater than some threshold, or perhaps you have somebody identifying parts of an image that represent, a cat or a dog, and you want to cut out that part of the image and specify only the image and not its background. And so fancy indexing gives us a way to do things that aren't these regular, step sizes or just little blocks that are going to come out in the exact square we want. So let's take a look at how that is done. Let's scroll up here a bit. So we're going to create a new range, and we're going to say we're going to go 0 up to 80, but not inclusive again. And so step by 10. So got 8 numbers in there ranging from 0 to 70. And what we're going to do is specify some indices as just a list of numbers or positions that we want to pull out. So we'll pull out the thing at position 1, thing at position 2, and then the thing that is 3 positions from the end, whatever they happen to be. And so 0, 1, 2, and then -1, -2, -3. So we should get a 10, a 20, and a 50 out of this when we go ahead and slice. And so we're going to basically say y is equal to a of indices. And so when we look at y, we now have 10, 20, and 50. So by specifying the indices, we can basically grab anything we want. So let's just play with that a little bit. You don't have to set it up in a variable. We can just say I want positions 1, 2, and 3. And so it's this nested list. And in fact, I can specify the same thing multiple times if I want to. And it'll go grab, the thing in index 1, then the thing in index 2, then 3, then back to 1. And so I can use this to reorganize my array, duplicate things in the array, a lot of different possibilities simply by specifying the index that I want to about that. If I want to, again, look at A and start assigning things to A, say, I need to put in a special value at my index locations. If you remember, they were 10 or 1, 2, and -3. I can basically insert those values into the array at 1, 2, and -3, so that those all go into that particular array. We can do the same sort of thing, that instead of specifying the indexes, we can create a Boolean mask. So I'll show you how to do that. And we're going to just put in 0s and 1s in all the things that we wanted to select. And so this is going to be just like the indexes, but with a Boolean mask, dtype equals Boolean. And so now we have our mask that we're basically going to say, I want to grab the stuff where it's true and ignore the stuff where it's false. And so now if I look at A of mask, I'm going to just grab those 99s that we had, because those were in the, false, don't grab that, true, grab that, true, grab this one, skip the next two because they're false, grab this one because it's true, skip the next two because they're false. So basically match that array to the A array by position so that you can see what's going on, and then it just grabs the pieces that are true. Okay, and again, we can have Z equals A of mask, and we can print Z, or just type Z to in IPython to get it so that we can take a look at what's going on with it. Okay, so let's go and look at a slide that has some more examples. So fancy indexing in 2 dimensions can be, a little more involved in terms of getting started. And so when I index in 2 dimensions, notice that I'm putting a list of indices, comma, a list of indices. And if you remember, in 2 dimensions, we're always doing row, comma, column. So this is, the first one is row indexes. So I want to grab from 0, 1, 2, 3, and 4. And then the column indexes, I'm starting at 1, 2, 3, 4, and 5. And so in terms of the points, I'm basically looking at what is 0 and then 1. That gives me that. Row 1, column 2 is 12. Row 2, column 3 is 23. Row 3, column 4 is 34. And then row 4, column 5 is 45. So when I try and line these up, now you think about them as rows, a row list and then a column list. But if you can visually imagine in your head where I'm lining up the 0 and the 1 and the 2 and the 3, that's what's giving me the coordinates that are pulling things out of here. And so these 2 lists have to be the same size because I need a row coordinate and a column coordinate for each element that I'm pulling out. Okay, so that's the yellow one. The blue one, we're going to mix indexing. So in the rows, I'm grabbing all the rows from 3 to the end. So all of this stuff from 3 to the end. And then I'm doing fancy indexing by passing a list of the column indexes from which to grab those rows. So I want the rows from 3 and above, but only in columns 0, 2, and 5. And so that's going to pull out the stuff that's outlined in blue. And then as an example of using the mask, we're now creating a mask with these Booleans. So I'm only interested in the 0th element, the one at index 2, and the one at index 5 in terms of the rows. And then I'm going to pull the entire column, which is column 2. And so that's going to pull out the 2, the 22, and the 52. So there are 3 true values or 1s here. And so I'm expecting 3 values out of there for, 1 for each row that I've selected because I'm only picking out 1 column. Okay. One of the things to note is because we're doing fancy indexing, whenever you get the fancy index, so here's Z. If I do Z of 0 equals 1, I affect Z, but I don't affect the original A. Fancy indexing always produces a copy. You don't have to tell it to produce a copy. And it's basically because there's no underlying pattern that you could create a view from easily that would allow you to use the same memory. So Z Anytime we do things with fancy indexing, you're creating a new array that is not linked to the original one. Okay, any questions before we move on to the next piece? Okay, not hearing from Alex. Let's go ahead and do this, give it a try. And that'll allow you to play with fancy indexing for a bit. And so let's take that until about 12:23 so you can play with getting the blue elements, and then we'll see if anybody can figure out question 2. If not, we'll go over that.
Just answering a question from the chat. Yes, the size of the mask has to match the dimension that you are indexing. So if there are 4 items along that dimension, you need 4 elements in your mask. Hasn't yet realized. Eric, did you give a tip on the divisible by 3?
No, I did not give a tip on the divisible by 3. But I can give one right now. So if we have our array, I can index with a mathematical operation, where if I say A is greater than or equal to 99, so in that example, I will get this creating a mass for me. And if I want to see what's happening, greater than or equal to 99, I can see what's being created for the mask. And then I'm putting that mask in the index and pulling out the pieces that I want to pull out. So if you can figure out a mathematical operation for divisible by 3, instead of typing in the entire mass, you can actually do it that way. give you another minute to maybe absorb that tip and play around with it, and we'll jump into the solution. Okay, so I'm going to set up a new A as in the slide. So we're setting up the same 5 by 5 array. So that's what A looks like. And so now I want to get this set up so that I can pull out the blue section. And so I'm going to just set up a variable called rows, which is just going to be my row indices. And so I want 0, 1, 2, and 3. That one's the simple one. And then columns, we're going to set up as I want columns 1, 2, 3, and 4. So that now I've got the corresponding coordinates of my setup. And so now I can basically put in rows, comma, columns, and it'll pull out 1, 7, and 13. And so you can see what's going on. This is going on under the covers where it's zipping the rows and columns together by position, and we're getting to coordinate 0, 1, then grab coordinate 1, 2, grab coordinate 2, 3, and 3, 4. And so we're just lining those rows and columns up with each other and producing these coordinates so that NumPy can then pick out each element that we want to pick out. Okay. Now for the second piece, we want to get all the numbers divisible by 3. You know, we could go in and start typing in a mask, which is NP array of double rows, and then essentially type in 5 lists of Boolean values and then do the D type. And inevitably, if you type as badly as I do, make a lot of mistakes, have to go figure it out. So there's got to be a better way. And so if we look at A, we can basically check A for, you know, is something greater than 23. You know, there's the mask. We can cut that down to 22. So we can do a lot of different things with a mask. Say, where is it equal to 4? There's 1 point there, one where it's equal to 4. So to find things that are divisible by 3, I need to be able to do modular arithmetic. So take the modulus, which in Python happens to be the percent sign. And if I do A mod 3, I'm going to be able to figure out where if I divide every element of the array by 3, what am I going to get as a remainder? And all the ones that are divisible by 3, the remainder is going to be 0. So I create my mask by doing A mod 3 is equal to 0. Note the double equal sign. That's, you know, checking if it's equal rather than assigning 0. And so that's going to pull out those elements. And so I can just say the mask is equal to A mod 3 is equal to 0. So there's my mask. And now A of mask will pull out all the stuff that's 0. But again, I can say a mod 3 is equal to 0 and have that as my index. It's going to produce the mask, and then the mask is what gets indexed. And so now if you can find a pattern in your data in terms of what you want to pull out, that's the best way to create a mask. And so now if you're processing an image, you might have some threshold color value where, I don't know, say you're doing a grayscale image and you want all the stuff that is, near white. You can say, give me a where, the color is greater than, I don't know, 100, and it'll pull it out. We don't go up to 100 here, so say up to 15, and it'll create a mask for us based on the values in the array. And then you can apply that mask to do whatever processing you need to do to set things up for yourself. Okay, any questions out there in the wild, Alex?
Yes. Could you scroll up and explain what zip was for again?
Okay.
Or why you used zip and how it's useful in this case?
Well, it's useful in this case basically to show you what's happening in terms of the coordinates. So if you remember, I did A of rows, comma, columns. I could also have just typed all of this in manually and at 4, get everything right. Oops, there we go. And get the same result. But I find, matching things up is, people don't often understand that I have to put a list of row indices and then a list of column indices, and how do they relate to each other. And by zipping them and turning it into a list, if I just zip rows and columns, I'm going to get this zip object that doesn't really do anything. So I create a list of the zip object, and it's basically telling me exactly how things are lined up so that row 0, column 1, and I can go down here, row 0, column 1, that's the first blue, and then do the next thing with each one. And that's simply for my benefit so that I can see how my rows and columns are matching up, because I tend to think point by point in terms of picking out the cells rather than, oh, here are all my row indices and here are all my column indices. And then I have to do some mental magic.
So it gives you the pairwise coordinates of each cell of each point. Okay.
We're not indexing with that. It's just useful for us to understand what's going on.
Got it. There's a question. I don't know how to ask this. So that was in the previous slide, I think. Can you go back to the previous slide?
Sure.
Yes. So that particular slide doesn't have the start code. In a sense, like there isn't the code used to create this array. I'm going to paste it in the chat now. It takes advantage of a feature of NumPy. Maybe Eric will get to it. I won't promise it, but it's called broadcasting. So I'll just give you the keywords that's in the Slack now. So I pasted the code that will create the array called A. And then executing the code that's in the slide should give you the same output. So that's it for now, Eric. Oh.
I'm going to copy it into my IPython session.
Okay.
So that you can see that. And then that way it'll be in my history log so that you
got it. Yeah.
It.
One more question. If you have A and you do A modulo 3 equals 0, there is nowhere where we specify the D type to be Boolean. Does it happen magically? Or like, let's not say magically, let's say automatically.
So if we do A mod 3, we're still in D type integer. If we do A mod 3 equals 0, the equals is going to produce Booleans. And so you're automatically going to get a D type. So let's say mask is equal to A mod 3 equals 0, and mask.D type is Boolean.
Got it. Thanks.
Okay, so I'm going to go back and look at one more slide right here. There's the slides again. So we did that exercise. Now, in terms of different dimensions of arrays, so we've got the one-dimensional, 2, 3, and 4-dimensional cases. This slide's helpful for visualizing things. And so if I focus on the one-dimensional case over here on the left, this is the shape tuple that comes out that basically says we only have 4 columns in this. It's a vector, and that's what gets added on. When we go up to the 2-dimensional case, notice that we start inserting things at the front of the tuple so that now we have 2 rows and 4 columns. Here we have 3 depth, 2 rows and 4 columns. And then here we have sort of 2 3-dimensional spaces, 3 depth, 2 rows and 4 columns, so that our tuple is telling us what's going on, and just depending on what dimensional case we're looking at, we're always adding things to the beginning of the tuple in terms of the way we visualize the dimensions in NumPy. And so the axis for the columns here is axis 0, and it's just the index of that element in the tuple. And see, in the 2-dimensional case, we have 4, which is our number of columns, is in the 1 position. So the columns become axis 1 and the rows are axis 0, and so on. Notice that if we look at this in the negative index space, the columns are always going to be at index -1. And so you'll often see people who work regularly in multi-dimensional space counting from the end of the tuple in terms of figuring out which axis they're talking about in terms of the way we visualize these NumPy arrays, of always using -1 for the columns, -2 for the rows, -3 for the depth, and -4 for, say, a time dimension. So that diagram's just there to help you visualize things and then to see what axis is going on. So the top axis, excuse me, is counting from the beginning, and the bottom axis nomenclature is counting from the end of the shape tuple that we can always get. So for any array, m.shape will tell us, now this is a 5 by 5 array, 5 rows, 5 columns. 5 rows, 5 columns. Excuse me. Okay.
Eric?
Go ahead. Yes.
One question. This is a very important question. I'm going to promote it to an actual question, and I'm going to click the button. Is 1, 4 the same as a 4, comma? as for the shape?
No. They're
good. So we can move on.
Okay.
No, it's a joke. Please give a little bit more details than just no.
So let's create an NP array with 4 elements in it. So a.shape is 4 comma, and now we're going to do the same thing with b. So we have a separate example, and then we're going to do a reshape of 1 comma 4. b.shape. If I look at the number of dimensions in A, it's 1. The number of dimensions in B is 2. And so you're going to, basically you're just, yes, they both have 4 elements in them. They both happen to be the same 4. But you can see that in the printout, they're actually represented as B is a 2-dimensional array, but only with 1 row in it to interpret the dimensionality of the system. And so I can say, give me B of 0, and that'll give me the whole row that is that 0th row. But A of 0 is only going to give me a single element because we're back to the 1-dimensional case with A, because it only has 1 dimension, but B has 2, even though there's only a single row in that row dimension there. So I think that pretty well covers it.
Yeah.
Okay. So let's just go ahead and talk about some of the mathematical operations in creating arrays, or things you can do with arrays. I'm going to actually, because of time, we're going to skip some of these, but we've already seen a lot of these. We've seen arrange, we've seen linspace, we've seen create the array out of a list. You can also create arrays full of zeros or full of ones. And so, given what you've seen, you don't need to go over that again, and we can make better use of our time by looking at some of the array calculation methods. Okay, so one of the most useful things about a NumPy array is not only can we do element by element calculations, but we can actually start adding arrays together, getting stats on them, and doing a variety of operations. So when we're doing these computations, there are 4 main rules that we have to think about. Rule 1, if I do operations between different array objects, it's first going to check that they're of compatible shapes. I can't add a 1-dimensional array to a 2-dimensional array or a 3-dimensional array. It's or something that there's the wrong number of elements in a certain dimension. So it's going to check for that first. Then, assuming the shapes match, then any of the plain mathematical operators, plus, minus, times, divided, exponentiation, doing the logarithms, the sine, whatever we're doing with the array is going to happen element by element on each value in the array. So NumPy goes back into the background, does all the loops through the entire arrays as needed for us, and applies those mathematical operations. Then we can do a whole bunch of what are called reduction operations. So getting the mean of something, or getting the sum, or the max, or whatever statistic we want, it's going to apply that reduction operation for the whole array, unless we specify one of those axes that we talked about, where we can say, I want to give me the mean of this array along axis 0 and only get the means for all the rows or all the columns by specifying the axis. And we'll talk a little bit more about that. And then there's something in NumPy called a not a number, and it's written np.nan. So what that's used for is as a placeholder where you don't have data, and basically any of the operations that you do element by element, if one of them is not a number, then the resulting operation will be not a number. And then same thing will happen to the reduction operations, that it'll create issues there with the way the reductions work. So you'll get warning if there's these placeholders in your data to do things. So let's go ahead back to IPython and just take a look at some of these. So I'm going to create a two-dimensional array. 1, 2, 3, and 4, 5, 6. So essentially 2 rows and 3 columns. And so let's just grab the sum of that. And so I just do a.sum, and it's going to add up the entire array for me. So that's 21. If I go ahead and do a.sum and specify an axis equals 0, it's going to add these up, and I essentially get a new row of data out of the system. So it added 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. If I look at the shape, axis 0 is go ahead and sum by the rows. So we've specified 2 rows, so we're going to add each row to each other. So that's why we're doing the row-wise addition. If we specify axis equals 1, instead of adding the rows to each other, now we're going to add the columns to each other, and we're going to get 2 values out of this. So essentially a new column. And so 1 plus 2 plus 3 is 6, and 4 plus 5 plus 6 is 15. So you're able to control, do you want to add up rows? Do you want to add up columns? Do you want to add up the whole thing? Okay, so there's lots of other operations.
Eric?
Go ahead.
Can you show slide 30? Did you show slide 39? Did I miss this? I think it's a good visual summary of what you just described, where people can see the before and after in one place plus illustrations.
Yeah. So just in going through that, again, that top one is just the sum of the whole array. And the next one down, we're specifying axis is 0. So it's adding up down the rows. So 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. And then in the axis equals -1, so they specified in the slide the negative version of the axis, so it's going along the columns. And so 1 plus 2 plus 3 is 6, 4, 5, 6 is 15. So you can basically control exactly what you're trying to get.
Great. Thanks, Eric.
Mm-hmm.
Just FYI, you have 10 minutes left.
Yeah.
So you can pick wisely what you cover next.
Wisely. And at the end, you get to tell me whether I chose poorly or not.
Yeah, but I'll do that offline.
Okay, so just so you know, there's lots of different ones. We can specify the axis on any of these as well, so that we can do the max along the rows or along the columns and so on. So there's a slide showing you the different operations you can do, and you can play around with all of those. The one that we really ought to spend time with here is this argmin and argmax, because what it's telling you is not the minimum value. It's going to tell you where the minimum value occurs, and there's a little bit of a need to unravel that. So I'm going to just a min is going to tell me what the minimum value is, and it happens to be 1. And then if I do a.argmin, it's going to give me a coordinate for that, which is that it is in position 0. Now, one of the things you have to worry about on argmin is that it's giving you a one-dimensional coordinate, as if you basically lined up all of your rows end to end and counted. So again, a.max is going to give me a 6, and a.argmax is basically telling me it's in the 5th position. So 0, 1, 2, 3, 4, 5. So the way we deal with this is there's a special function called unravel index that's part of NumPy. And we can say we want to unravel 0, and I'm going to pass in the shape, and you tell me what that coordinate is for that particular shape. That's 0, 0. So row 0, column 0. And if I pass in my argmax index, it's going to tell me that's in position 1, 2. Now I can put all that together and just say a.argmin, figure out where that is, or a.argmax, and figure out where that is. And it's just, that's one important thing, that when you're trying to locate the minimum or the maximum in your array, as opposed to knowing what the value is, setting it up with this NP unravel index is the way to go, because unless you're dealing with a one-dimensional array, it's going to give you a coordinate that is, in a sense, one-dimensional, and you want normally to have the coordinate match whatever shape your array is, and that's the way to sort that all out for you. Okay. Let's do another function where we're going to do np arrange. We're going to say -2 to 2, and we're going to raise it to the 2nd power. So we've got this one-dimensional case with those elements in there. And if I want to find out the things that are divisible by 2, I can essentially do my modulo 2 is equal to 0, and I can set up a mask that has a modulo 2 equals 0. And so if I do a of mask, I'm going to get the actual values out. Whereas if I do np where of mask, I'm going to get the coordinate locations where that mask is true. So position 0 and position 2. And so just like argmin and argmax, this where function is going to give you, you put your mask in, it's going to tell you where it's true, so that it's easy for you to figure out where things are if you want to see that. Now, the where function is used in another case, which is kind of interesting. So we're going to create a positives array, which is NP range 4. And we're going to create a negatives, which is going to simply be minus the positives. So positives looks like that, and negatives looks like that. So now, if you remember, I have a mask that's going to pick out the 0 and the second element. And so now if I do npwhere mask and put in 2 arrays, one's my positives and one's my negatives, what it's doing here is it's saying where the mask is true, get the value from the positives array, and where the mask is false, get the value from the negatives array. So very powerful technique to pull things out. I could just put a number in there in either position so that, I want to get rid of my negatives or I want to get rid of my positives. I can basically use this where function in conjunction with a mask and say, this is what to put where it's true, and this is what to put where it's negative. If it's a scalar, it will be put in every value. And if it's an array, it'll pick out the things out of the right position for that. And so with that, I think I'm about out of time, and I was asked to make sure everybody got this survey. I don't know, Alex, what's the best way to get this to everybody in Slack? So there's a survey for NumPy that they do every year that they want to know how people are planning to use it or that they do use it, and features you're interested in, because it's continually evolving and getting better and better. And this gives you a way to let the NumPy developers know, how it's working for you and things that you would like to see.
Mm-hmm. Is there a link?
Yeah, I could. I was trying to be helpful and give you the whole text. There's a link.
All right, so let's paste the whole thing in Slack, but share the link right now in the chat.
There's the link right there. And we can paste the whole thing in Slack. There's my Slack channel, tutorial NumPy, and there's the whole thing.
With the link also.
Oh, come on, Alex, you're so picky. Copy link address.
Well, while Eric pastes the survey in the Slack channel, thank you everyone for joining. Eric will export his history sessions and put them on GitHub. We'll be looking at the NumPy channel over the course of the conference. So if you have outstanding questions, you can go in there and ask questions. I will do our best to respond. And I will see, I think I should be able to export the chat. And so I'll try to do that and also put it on GitHub together with the history. So
that's a good idea. So
thanks everyone.
In the history folder.
Yeah. Thanks a lot, everyone. And I hope you have a good rest of your day. I hope you can have a good night for people who are in the middle of the night, and enjoy the rest of your conference.
Thank you.